So, in the last class I have discussed that how we can determine the bearing capacity of that wrap foundation resting on the clayey soil, and then it is observed that the factor of safety that we are getting for bearing capacity consideration is 7.1, which is greater than 2.5, and basically it is over safe. Now, in this class I will discuss that the second part, that is the settlement calculation. So, this is the profile, soil profile that was taken, and for the bearing capacity consideration, the influence zone was your 14 meter, which is B, and for settlement calculation it will be 28 meter. Okay. So, that will be just close to the end of the third layer. So, up to 29.5 meter from the surface. Okay. So, now and we have taken the weighted average, because the variation is not that significant for the Cu value or the strength parameter, and now we will do the settlement calculation. So, the settlement calculation. So, Q net, which is 58.3, which is coming at the base of the foundation, and B value is 14 meter, and depth of foundation is 1.5 meter, and water table also at 1.5 meter from the ground surface. So, here we have to first calculate the immediate settlement. Okay. So, that equation I have given for clay immediate settlement and consolidation settlement, I have given the 2 equations, and for sandy soil I have given the 5 equation to determine the settlement. So, for the clay soil immediate settlement, which is the elastic settlement, Q n B 1 minus mu square divided by E, and then I f, influence factor. So, here also what E value will consider. So, here also weighted average E value will consider. So, E average, like the previous case, because we consider the weighted Cu value during the bearing capacity calculation. So, here also we will use the weighted value, weighted average E value. So, that value is here, you can see the first layer it is 3.5 meter, then the total 13 meter for the second layer, and for the last layer it is will be 11.5 meter. Okay. So, and again I want to mention that if your influence zone is going to that rigid portion, that means if it is below the 30 meter part, then you have to consider up to 30 meter. Okay, that I have discussed during my settlement calculation part. So, that means here influence zone, if it is in the rigid zone, then we will not consider the rigid zone, we will consider the portion above the rigid zone. So, that means here average E value will be 4200 into 3.5, this is for first layer, then 4900 into 13 for the first layer, then 56000 into 11.5 for the third layer, because now it is settlement, influence zone is 28 meter from the base of the foundation. So, then it is 28. So, this is 51,000 kilonewton per meter square. So, I can get the Q n is 58.3, B is 14, and mu value is taken as 0.5, because we have the table from where you will get the mu value. Mu value for the clay, saturated clay is 0.4 to 0.5. So, I have taken 0.5. Okay. You can take 0.45 also, but if exact value is not given, then you can take the value from this range. So, I have taken 0.5, and then weighted average E is 51,000, Now, the IF influence factor. So, influence factor table is given. So, here what I am considering or I am taking that it is a raft foundation. So, it is a rigid foundation. So, directly I can take the IF for the rigid foundation, but as I will later on apply the rigidity correction for consolidation settlement. So, that is why I have decided I will take the center IF for flexible foundation, then I will apply the rigidity correction of 0.8. Okay. So, as I have discussed that this rigid foundation IF value is 0.8 times of the flexible foundation IF value at the center. So, for the this is for the square footing, this is for the center for flexible foundation 1.12, then I will apply the rigidity correction, then I will get the settlement for the rigid foundation. So, this is 1.12 I will use. So, this is IF is 1.12 for square foundation. So, this is 1.12. Okay. So, this value is 13.44 millimeter. Now, we have to apply two corrections. Okay. So, these corrections, one is the rigidity correction, factor, which is equal to 0.8. So, now remember that if you directly take the influence factor for rigid foundation, then this rigidity correction is not required. But here I have taken the influence factor for flexible foundation, that is why I am taking applying the rigidity correction. Because later on in consolidation settlement calculation, whether I take the IF value for flexible or the rigid, I have to apply the rigidity correction for consolidation settlement. Okay. So, that is why I have used here the flexible foundation IF, so that I can apply the rigidity correction of 0.8 here also. Okay. So, rigidity correction factor and then the depth correction factor. So, that value is how much? So, I will use this chart. So, this chart is d by L root over L by B. So, this is d by root over L B. So, d is 1.5, root over L is 1.4 into 1.4. So, that means 1.5, sorry, this is not 1.4, this is 14, because L is 14, B is also 14. So, this is 14. So, this value is 0.11 and L by B is equal to 1 for square. So, 0.11, this is 0.1, this is 0.11 and this is for 1. So, this is for this chart is for 1. So, this value is roughly correction factor is 0.96. Okay. So, this correction factor is 0.96. So, this will be the value. So, correction factor will be 0.96. So, I can go the depth correction factor is 0.96. Okay. So, the immediate settlement corrected, that will be 13.44 into 0.8 into 0.96. So, that is equal to 10.3 millimeter. Okay. So, the immediate settlement corrected is 10.3 millimeter. So, next part I will calculate the consolidation settlement. So, next part is the consolidation settlement. Okay. So, that consolidation settlement equation is given. So, that is summation of Cc 1 plus E 0 H log 10 P 0 bar plus del P divided by P 0 bar. Okay. Now, for this purpose, remember that, because here we have assumed that this is the total range of the stress, the soil is normally consolidated soil. So, there may be a possibility the soil may be in the over consolidated range. So, in such case C c you have to replace with, this is the compression index. So, you have to replace with swelling index, and there is a possibility case that initially the soil was in over consolidated stage. Now, when you apply the stress due to the external load, the soil will go to the normally consolidated stage. So, in that case it will be the some portion will be your C c and some portion will be the swelling index. So, based on that you have to determine this consolidation calculation. So, here it is in normally consolidated soil. So, I have to use the total range is C c, and then so for that purpose we have to divide this settlement range into 3 zone we have taken. So, we have to take the point, the middle of each layer. This is A point, this is B point and this is C point. This is the middle of each layer. So, this layer, this thickness is 3.5 meter divided by 2. Okay. So, this thickness is 3.5 meter divided by 2, which is 1.75 meter, and this one is, this is 13 by 2, it will be 6.5 meter, and this one is 11.5 divided by 2. So, this is 11.5 divided by 2. So, this will be 5.75 meter, 11 meter thickness for the third layer, 11.5 meter thickness. So, this way we have selected 3 points. So, now I have taken only one point at the center of the layer, but as I discussed that you can take multiple points also. So, you will get slightly better result, okay, more accurate result, but here I have taken one and which is sufficient. So, now we can go for this equation, you have to apply the every point A, B, C. Now, for at point A, your P 0 bar is equal to that, for the top layer it is 1.5, then it is 18 where water table is not present, that is above the water table. Then we will go for the submerged unit weight, and that is 18 divided in minus 10 into 3.5 divided by 2, that means 1.75. 3.5 divided by 2, 1.75, and that is equal to 41 kilonewton per meter square. So, del P I have taken 1:2 distribution. So, del P is 58.3 into 14 into 14, then 14 plus 1.75, then 14 plus 1.75, because we have taken 1:2 distribution. So, this is 46 kilonewton per meter square. Similarly, point B, P 0 bar, which is again 1.5 into 18, then 1.5 into 18, then 3.5 into 8, then 6.5 into 9. Okay? Then plus 3.5 into 18 minus 10 plus 19 minus 10 into 6.5. So, this is 113.5 kilonewton per meter square, and del P is equal to 58.3 into 14 into 14 divided by 14 plus 3.5 plus 6.5, because this is 3.5 plus 6.5 is the distance of the point B from the base of the foundation. So, this is 14 plus 3.5 plus 6.5. So, this is equal to 19.84 kilonewton per meter square. Similarly, at point C, P 0 bar is equal to 1.5 into 18 plus 18 minus 10 into 3.5 plus 19 minus 10 into 13 plus 19 minus 10 into 5.75, which is equal to 224 kilonewton per meter square. So, del P will be equal to 58.3 into 14 into 14 divided by 14 plus 3.5 plus 13 plus 5.75. Plus 13 plus 5.75. So, that is equal to 8.7 kilonewton per meter square. So, we have calculated the P 0 bar and del P. Now, we have to apply this with the equation for every point. So, S C is equal to, for first layer 0.08 and thickness of the first layer below the foundation is 3.5, then log 10, this is 41 plus 46 divided by 41. Then for the second layer 0.06 into 13 is the thickness of the second layer, then log 113.5 plus 19.84 divided by 113.5. Then for the third layer 0.04 into thickness is 11.5, then log 10 224 plus 8.7 divided by 224. Okay. So, separately if I calculate that, it will be 91.5 plus 54.6 plus 7.6. So, total settlement is 153.7 millimeter. So, this is uncorrected. So, we have to apply the corrections. So, what are the corrections? So, again the corrections are so for depth correction, this factor is 0.96, and remember that when I discuss the example problem or the plate load test, then I discuss that if the depth of the plate and depth of the foundation is different, then when you apply this depth correction, in that case D will be the difference between the depth of the plate and depth of the foundation. So, that will be your D. Based on that, you have to apply the correction factor. Okay. So, and then we have a depth correction factor is 0.96, and then rigidity is 0.8, and remember that the design of shallow foundation or isolated footing is same as the design of wrap foundation. Only difference will be, in that case we will not use the rigidity correction, okay, because that isolated footing you consider as a flexible type of foundation, and the wrap foundation is a rigid type of foundation. So, this is correction. Now, the third correction you have to apply, which we did not apply in the immediate settlement, that is the consolidation correction. Okay. So, that is your that is the pour water pressure correction, that is the pour water pressure correction, and that value we will take that from the chart you can see we have a chart. So, we can use the square footing part. So, that correction factor you can see that for normally consolidated soil. So, this is the normally consolidated soil range, because here A value is not given, and during that my class I have discussed that if nothing is given, then for normally consolidated soil you can take 0.7 as the correction factor for pore water pressure. So, here this is normally consolidated soil, this is the farm line. So, we can go this range. So, this range is from 1 to point, this is the range. So, 1 to around 0.6. So, this is the range actually. So, for normally consolidated soil for square footing, so this is the probable range. So, which varies from 1 to, this is the lowest value, which is 0.65. So, this is I can say 0.65 and this is this is 1. Okay, this is 1, and definitely it will be this line, because your H is the thickness of the layer below the foundation base, and with B, and thickness of the layer is here, it is twice B. So, this means we are taking the thickness of the layer say twice B, and this is B. So, this is 2. So, 2 means this is 4, this is 1. Okay, so, that means this value will be somewhere here. So, this value we can say this is 0.6, this is 0.7, this will be around 0.67 or something. Okay. So, this is the range, but it can be in this area also, but here no information is given. So, that is why I have taken it is the lower range. So, roughly 0.7 I am taking, but if this A value is given, then from this chart you can determine that what would be the probable correction factor, but if nothing is given you can take 0.7. So, here also you can see that for normally consolidated soil it varies from 0.65 to 1, and we are taking around 0.6. So, which is reasonable, but if you have this A value particularly, then you should get that correction factor which is actual correction factor, but here I have taken 0.7. Okay. So, I have taken 0.7. So, my SC corrected, which will be 153.7 0.96 into 0.8 into 0.7. So, which is 82.6 millimeter. So, total settlement considering consolidation and the immediate settlement, this will be 10.3 plus 82.6, that is equal to 92.9 or close to 93 millimeter, which is less than 100 millimeter, which is the permissible settlement as per IS code for wrap foundation resting on the plastic clay. Okay. So, that means it is safe. So, but it is not over safe, it is properly safe, I should say, because it is not over safe, not this value is exactly close to 100. So, that means we can say that even if it is over safe against bearing, but in settlement it is not over safe. So, the dimension that we have chosen for the first trial, we can provide that dimension of the foundation. Suppose this settlement is greater than 100 millimeter, then we have to then again do the second trial with new dimension, and we have to check whether the footing is safe or not. That means, we have to increase the dimension in that case, and we have to check whether the foundation is safe or not against settlement. So, that means, here this particular case the settlement is the main design criteria, because it is mainly controlling the design, okay? Because your settlement is just safe, but bearing capacity is over safe. So, that is why we will provide the dimension that we have chosen for the first trial. So, this way we can provide the dimension of the foundation which is resting on clay. So, I have discussed the foundation which is resting on sand. Basically, I have used the field test data in such case, and then I have discussed how we can design a foundation resting on clay. And then once you get this dimension, then you can consider that the soil structure interaction part, and then also you can get the bending moment and the shear forces also, and then considering the soil structure interaction also, you can see whether the settlement that you are getting without considering this soil foundation interaction, and then the settlement that you are getting considering the soil foundation interaction are close or not. So, that check also you can do. That means, once you get this dimension, then you can go for the the soil foundation interaction part that I have discussed, and then you can determine the bending moment and shear force also, and then the other parameters. And remember that in this particular course I have discussed only the beam resting on elastic foundation, because I have given the concept of that soil foundation interaction, because the detailed discussion is not the scope of this course. Okay. So, but in that beam you can use for model some different types of foundation, like the strip footing I have discussed. The strip footing, if the you can model it beam with infinite length, and you can model with beam with finite length. Okay. So, that means you can model beam under plane strain condition for strip footing, when the beam with infinite width, and then you can model the beam with your beam with finite width also. Okay. So, in those cases you can use the beam on elastic foundation concept, then you can use it for the for your railway track, all these cases for combined foundation, for strip footing, railway track. So, those cases you can use that beam on elastic foundation concept. But suppose if you are doing a rectangular or square raft or the circular raft, so in those cases you have to use the plate on elastic foundation. So, that means, but that concept I have given, that beams on elastic foundation. So, that is a similar concept, you can use it for the plate, and then you can analyze. So, because the scope of this study to introduce the soil foundation interaction, it is not a total course of soil foundation interaction. So, that concept I have given, but remember that sometimes only beam concept is not sufficient, you have to go for the plate also, but the concept is similar. That means, the concept that given for the beam. So, that you can use for strip foundation, combined footing, but sometimes you have to extend your beams on elastic foundation concept to plates on elastic foundation by using the same concept. So, that you remember before you do the check for considering soil foundation interaction. So, that means, I have finished the shallow foundation part. That means, in the first module I have discussed the how to determine the soil properties by using different field test. Then I have discussed the bearing capacity calculation, then I have discussed the settlement calculation for shallow foundation. Then I have given you the concept of beams on elastic foundation. Then for the shallow foundation, how you can establish the interaction between the foundation and the soil, and then you can determine the bearing capacity, you can determine the bending moment, shear force, settlement of the foundation. Then in the last module, I have discussed that how you can use those concepts that I have discussed, that means the bearing capacity, settlement, and then the beams on elastic foundation, and you can design your foundation. So, here the design means I have discussed only the dimension or the proportion of the foundation based on the field and the laboratory data. Now, here from here also, once you get this proportion, you can determine the bending moment and shear force by using the soil foundation interaction, if that foundation is suitable for your beams on elastic foundation concept. Otherwise, you can use the same concept for plates on elastic foundation, and then finally, you will get the bending moment shear force, and then you can finally complete your structural design part also. But the structural design part is not the scope of this course. Here you will discuss only the proportion of the dimension of the foundation, and that I have discussed. So, in the next class I will start the new topic, that is deep foundation. So, first I will discuss the pile foundation, then the next topic will be the well foundation. So, in pile foundation I will discuss all different types of loading conditions, that means the pile under compressive loading, then lateral load, then the under uplift. So, in the next class I will discuss the first type of loading, that like pile under compressive loading. Thank you.